Section 10.7, special segments in circles, picking up with number 17. So C is negative 96. That's the constant term here. We'll substitute those values into the quadratic formula. So opposite of negative 8 is positive 8 plus or minus negative 8 squared is 64 minus 4 times 3 times C is negative 96 all over 2 times A, so 2 times 3. So let's just go through some steps of simplifying this. We would have 8 plus or minus 64. Negative 4 times 3 times negative 96 is positive 1,152 over 6. So let's add 64, 1,152, and we get 1,216 all over 6. Since x is a length, we only want the positive answer. So on our calculator, we'll take 8 plus the square root of 1,216 and divide that quantity by 6, and we get approximately 7.1. On 19, we have two variables to solve for. In order to solve for b, first we have to get a, because to solve for b we have these two chords, and we would have two variables in that equation. But we can solve for a because we have a tangent, which we know its length, and a secant where our variable is at. So the entire length of the secant would be 4 plus a plus 6, or a plus 10. So now we want to set up our equation from the theorem that says the tangent squared, so 10 squared is equal to the part of the secant outside of the circle, so 4 times the entire length of the secant, so a plus 10. From here, simplify and you get 100, and distribute and you get 4a plus 40. Subtract 40 from both sides, you get 60 equals 4a. Divide both sides by 4 and you get a is equal to 15. So now that we know a, we can solve for b. Alright, so we have two chords intersecting inside the circle. So we'll take the product of these two parts, so 6 times a, or 6 times 15, and set that equal to the product of these two parts, so 8 times b. So 6 times 15 gives us 90, and if we divide by 8 and round to the nearest tenth, we get approximately 11.3. On 21, we have two variables. It doesn't matter what variable we solve for first on this one, so we'll just go ahead and solve for c first. So c is part of this secant, so the entire secant there is c plus 9, and the outer part of that secant is 9. So we want to take the outer part times the entire secant length, and then set that equal to, well, we can't set it equal to the tangent squared here, or else we would have two variables in the equation. So we want to set it equal to the product of this secant parts. So we want to take the outer part, which is 11, times the entire length of this secant, which would be 15 plus 11, or 26. So simplify and distribute, And you get 9c plus 81 is equal to 286. So subtract 81. We have 9c equals 205, and divide both sides by 9. And we get approximately 22.8 for C. Now to solve for D. That's a tangent. So the theorem says to square the tangent length and then set that equal to something else that we have here. Since we have secant, let's take a look at this secant one more time. So we want to take the outer part, which is 11, times the entire length, 26. Now we just need to take the square root of both sides, and D is approximately 16.9. Number 23, we want to write a two-column proof of theorem 10.15, which says that anytime you have two chords intersecting in the circle, the product of the parts of one chord is equal to the product of the parts of the other chord. So specifically for this diagram, if AC and DE intersect at B, and AC and DE are therefore chords, then AB times BC will be equal to EB times BD. So the way that we're going to go about this proof is we're going to show that these two triangles are similar. Once we can show that these two triangles are similar, we can set up a statement of proportionality and cross multiply to get this product here. So we are given that AC and DE intersect at point B. So let's write that given fact. Now we have some inscribed angles. Angles A and D. Notice if you follow those two sides out, it intersects arc EC, as well as angle D also intersects that same arc. So two inscribed angles that intercept the same arc will be congruent. So we can say that A and D are congruent. Likewise, we can say that E and C are congruent. Okay, because those angles both intercept this arc, AD. Okay, so based off of this information, I have two angles of one triangle are congruent to two angles of another. Therefore, the two triangles are similar by angle-angle similarity. Just make sure that you write those in the right corresponding order. So A corresponds to D, B corresponds to B, E corresponds to C. Once those are in the right corresponding order, now we can write a statement of proportionality. So we're going to compare parts of the two similar triangles. Since they're similar, their corresponding sides will be proportional, which means that AB relates to DB of the other triangle. And that will be in the same ratio as if I pick another side of this triangle. So let's say EB over how it relates to this triangle, CB. So our statement of proportionality, from that statement we can cross multiply and get what we're trying to prove. So AB times CB goes here, and DB times EB is here. So that's just the cross product property, proving that the product of the parts of one chord is equal to the product of the parts of the other chord. On number 25, a two-column proof of theorem 10.17, which says that the tangent squared, the tangent length squared, will be equal to the outer length of the secant times the entire length of the secant. So specifically for this diagram, since JK is tangent and JM is secant, JK squared should be equal to JL times JM. So we state our given information. We're going to go about this proof in a very similar way. We're going to show that this triangle here is similar to this triangle here. By showing that those two triangles are similar, then we can write a statement of proportionality and cross multiply to get this result. So we have an inscribed angle KML, which will be equal to half of its intercepted arc, which is KL. Also, we have an angle formed by a tangent and a secant here, with its vertex on the circle. So we also have a theorem that states that an angle like that will also be equal to half of its intercepted arc, which once again is KL. So what I've stated so far here is just that. Measure of angle KML is equal to half the measure of arc KL. Measure of angle JKL is equal to half the measure of arc KL. And therefore I can substitute. So I can substitute the measure of angle JKL in for what it's equal to, which also shows up here. And now we have this new statement. So measure of angle KML is equal to the measure of angle JKL because they both equal half the measure of arc KL. By the definition of congruent angles, we can say that the angles are congruent because they have the same measure. Now I need another pair of angles. I can just use my overlapping angle by the reflexive property. It has to be congruent to itself. So angle J is congruent to angle J. JKL is congruent to JKM. Now I have two angles of one triangle congruent to two angles of another triangle, so the two triangles are similar by angle-angle similarity. From there I can set up my statement of proportionality. So in the same corresponding order, JK over JL is equal to JM over JK, and if I cross multiply I would get JK squared here and JL times JM there, which is what we wanted to prove. Alright, check it out. Hope that helps, and have a good one.